Dear good, Conas Tautu, hello and welcome. And I hope that wherever you find yourselves today that you are keeping well and staying safe in these challenging times. Now today we're going to look at an experiment that was quite common on Leaving Cert papers, but I have not seen it come up for several years now. And that's an experiment to measure the specific heat capacity of a liquid by what is known as the electrical method. This is not a very difficult experiment, and I don't think you're going to find it too challenging. A lot of the concepts and ideas that we have developed already in other experiments, you're going to find are repeated here again. So let's go. Now, by the end of this experiment, I expect you to know the following. The experiment is about to measure the specific heat capacity of a liquid by what's known as the electrical method, and you will need to know the following. You should be able to draw a label diagram of the equipment used in this experiment. You should know what measurements are taken in the experiment and with what instrument. You should know the formula to calculate the specific heat capacity and be able to use that formula. And you should know 5 or so precautions that will make the final result more accurate. One precaution in particular we will be focusing on, that is one you probably have not come across before, and that is about pre-cooling the water in the calorimeter and why that will lead to a more accurate result overall. At the end, I will ask you to do question 2, page 276 from the book, just to test your knowledge and the knowledge that you have built up by watching this video. So let's go. Now in this particular experiment, we're going to use a piece of equipment that you probably have not come across before and you're probably not familiar with, and that is known as a Joule meter. Now a Joule meter lives up to its name. Joules are the unit of energy, so a Joule meter in essence measures how much energy actually passes through it. It measures usually how much electrical energy actually passes through it. You connect one end up to a source of electricity, the electrical energy passes through the Joule meter and the electrical energy goes out the other side. You can use that electrical energy to power any particular piece of equipment or connect it to, in our case, we're going to connect it to a heating coil, and this Joule meter will tell you how much energy has actually been supplied to the heating coil. So a Joule meter is an instrument that measures how much electrical energy passes through it. Now to see the Joule meter in a circuit, let's just have a quick look here. Well, here we've got a 12-volt electrical supply, very much like the power supplies you've used already. The Joule meter is here. It measures the amount of electrical energy passing through it, and the electrical energy passes through this heating coil here. So what in essence happens is that electrical energy is being converted into heat energy. Now the heat energy is manifested by a rise in temperature of the water, so the water picks up heat energy, and the copper calorimeter that the water is in also picks up heat energy. So using the formulas that we've come across already, we can calculate how much heat energy is picked up, how much heat energy is gained by the water. We can also calculate with this formula how much heat energy is gained by the calorimeter. And we know how much electrical energy has been supplied to the heating coil, so we can actually say the following, that the electrical energy supplied, as seen on the Joule meter, is equal to the energy gained by the water plus the energy gained by the calorimeter. And we can use that equation to solve for things that we don't know. Now, like any heat experiment, there will be a certain amount of heat lost to the surroundings, and we don't account for that in the formula, but we try to minimize it. So we will be minimizing the heat loss to the surroundings by lagging the calorimeter, by putting a lid on the calorimeter, and when we use a thermometer, we'll use a thermometer of low heat capacity. Now here's a diagram of how the apparatus and equipment is normally set up in this experiment to measure the specific heat capacity of a liquid by the electrical method. Electrical energy is converted into heat energy by the heating coil. The heating coil will heat the water, so the water absorbs some heat. The water has gained a certain amount of heat energy, and we can calculate that with our formula. Similarly, the copper calorimeter that the water is contained in will also absorb some heat energy, and we can calculate the exact number of joules absorbed or gained by the copper calorimeter using our formulas as well. The amount of energy that is supplied will be written on the Joule meter, will be on the digital display of the Joule meter. We will be using a thermometer to work out the rises in temperature of the water and the rise in temperature of the calorimeter. Obviously, the masses of the water and the mass of the calorimeter can be obtained using electronic balance. It's not normally put into the diagram. And we are minimizing the heat loss to the surroundings using this insulation here, this cotton wool or polystyrene foam or something like that. We could also put a lid on the calorimeter, and obviously the thermometer would be a thermometer of low heat capacity. We discussed that before. So if we keep going down and look at the formula for this particular experiment, I think you will understand it reasonably well. Because the formula basically says the energy gained by the water plus the energy gained by the copper calorimeter will equal the energy supplied by the electrical source. And that, of course, will be registered on the Joule meter. So the energy that's supplied, we can measure using the Joule meter. The energy gained by the water, we can calculate using the mass by specific capacity by change of temperature of the water. And the energy gained by the calorimeter, similarly, will be the mass multiplied by specific capacity multiplied by change of temperature in the calorimeter. Now in the experiment, E will be measured using the Joule meter. The masses of the calorimeter and the water will be measured using electronic balance. The rise in temperature of the water, which of course will be equal to the rise in temperature of the calorimeter, that will be measured using a thermometer. If we know the specific capacity of copper, then the only unknown in our equation will be the specific capacity of water. And by filling into that formula, we can solve for C, the specific capacity of water, and we can actually put a number on it. Now, in the experiment, when we eventually do it, these are the measurements we'll be taking. The mass of the calorimeter, the mass of calorimeter plus liquid by subtraction. We will, of course, have the mass of the liquid, usually water, but not always. The initial temperature of the liquid and calorimeter, the final temperature by subtraction, that will be the rise in temperature, the energy supplied in the Joule meter, and we need the specific capacity of copper. Obviously, one big question comes to mind here. Do we use grams or kilograms? I've said in the past, you're never wrong if you convert to kilograms, but in most experiments you can get away with grams. It's actually easier to do it that way. In this experiment, you can't. You have to convert all your masses to kilograms. And the reason for this is simple. We've three parts, three parts in this equation. This part has mass in it. This part has mass in it. This part, the energy supplied as measured by the Joule meter, doesn't have mass, so you cannot use grams. You have to convert to kilograms. In the other experiments in heat, you can always leave it as grams. This is the one that you cannot. Now, here are some results that were obtained by students some years ago. They've got the mass of the calorimeter, mass of calorimeter plus liquid, etc., etc., etc. Very shortly, we'll be seeing how we can use these results to actually calculate a value for the specific heat capacity of water. But before that, we're going to look at some of the precautions that need to be taken to make this experiment and its final result more accurate. Now, these are ones that you've come across before, and they're not exactly that difficult. Precautions to make the final result more accurate. Lag the calorimeter with something like cotton wool to prevent heat loss to the air, to the surroundings. Better still, put a lid on the calorimeter as well. Use a more sensitive thermometer that measures to more places of decimals, or use a digital thermometer because that will obviously measure to more places of decimals. Use a thermometer with a low heat capacity. That means it will minimize the amount of heat it will absorb from the liquid it's measuring the temperature of. Polish the calorimeter to minimize heat loss by radiation to the surroundings. That, of course, is these are all very, very, very standard ones here. I'm going to stop there because now these are some results obtained by students some years ago in this experiment, and very shortly I'm going to show you how to use these results and put them into the formula to actually obtain a value for the specific capacity of the water. But before that, we're going to take a look at some of the precautions that should be taken in order to make the final result more accurate. Now, these are pretty standard ones, and I'm pretty certain you've seen these before. First of all, you should lag the calorimeter well to prevent heat loss to the surroundings, and also put a lid on the calorimeter. You should use a more sensitive thermometer, and that of course means one that measures to more places of decimal, or better still, use a digital thermometer, as that always measures to more places of decimal. You should use a thermometer with a low heat capacity, and that means that it will minimize the heat that it absorbs from the liquid, the water that it's trying to measure the temperature of. And you should polish the calorimeter to minimize heat loss by radiation. Now these four are pretty standard precautions, and I'm pretty sure you've seen them all before. But this one is a very interesting one. This is a new one, and this is one that's often focused on in Leaving Cert exams. And what this particular precaution is saying to us is that we should pre-cool the water in the calorimeter. And how would you do that? Well, you will place it in the fridge for some minutes before the experiment. And if you pre-cool the water in the calorimeter 15 degrees below room temperature, then allow the electric current to flow through the heating coil until the water is 15 degrees above room temperature, that will actually make the final result more accurate. Now, here's the reasoning behind it. If you pre-cool the water in the calorimeter to 15 degrees below room temperature, then if you pre-cool the water in the calorimeter to 15 degrees below room temperature, then it will start absorbing heat from the surroundings. If you then allow the electric current to flow through the heating coil until the water in the calorimeter is 15 degrees above room temperature, it will start emitting heat. It will radiate heat and lose heat to the surroundings. And the amount of heat energy gained from the surroundings when it's below room temperature and the amount of heat energy lost to the surroundings when it's above room temperature will be approximately equal to each other. So this is one that I think you should spend some time learning. The precaution is to pre-cool the water in the calorimeter to about 15 degrees below room temperature, and the reasoning behind it is that heat gained from the surroundings and heat lost to the surroundings will be approximately equal. That is the phrase there to learn and memorize. Heat gained from the surroundings when below room temperature will be approximately equal to heat lost to the surroundings when the calorimeter and its contents are above room temperature. Now this is also something that I have seen come up in Leaving Cert papers. It's a way to improve the accuracy of the result. Another precaution if you want. If the current is allowed to flow for a longer period of time, then this will give a larger rise in temperature of the water, and this of course, if you have you're dealing with larger numbers, you reduce your percentage error. However, there's a catch. If the temperature of the water becomes too high, this will lead to a greater heat loss to the surroundings, and then you're losing energy to the surroundings and your results become less accurate. A question I have seen come up in a Leaving Cert pre-paper. A question I have seen come up is back here. Sorry, excuse me a sec. Okay, we've lost it. Here we are. Why would using a greater mass of water while still supplying the same amount of energy be less accurate? Well, think about this. If you used more water in the experiment, if we go back to our diagram, have a quick look at that. If you use more water, a greater mass of water here, but you still supply the same amount of energy, what change will that have on numbers that you measure here? Well, the first change would be that the rise in temperature of the water would be less. If you use more water, it will rise in temperature by less. And of course, that will mean you have greater percentage errors, because the smaller your numbers, the greater your percentage errors. Okay, let's keep going. Now we finally get to the calculations, and here are some results that a student obtained in this experiment some years ago. We've got the mass of the calorimeter plus the liquid, which I presume is water. We'll see later at the result. If you subtract them, you get the mass of the water, the initial temperature of the calorimeter, the final temperature of the calorimeter plus the water. By subtraction there, you will find the change in temperature of the liquid, the water, and the energy supplied. You notice the energy supplied is 2.62 kilojoules. Now 2.62 kilojoules, 2.62 thousand joules, that is 2,620 joules. Because remember, kilojoules to joules, you have to multiply by 1,000, and it's joules that go into the formula. Now I always like to do a little bit of working out before I start the question, and look here at my working out. Well, here is the mass of the calorimeter plus liquid. Here's the mass of the calorimeter. I've now converted them to kilograms. I subtract, so this here is the mass of the liquid in kilograms. The temperature, the final temperature of the liquid was 25. The initial temperature of the liquid was 12. By subtraction, I've now got the change in temperature of the liquid, which is 13 degrees Celsius. And of course, if the liquid changes by 13 degrees, the calorimeter that surrounds it will also change by 13. They're always the same. So I've got my two values there. Now I am going to put all my values into that formula. Just scroll up here for a second and see what's going on. Now, the energy supplied was 2,620 joules. It was given to us in kilojoules, but we multiplied by 1,000 to get to that. The mass of the water goes there. The specific capacity, when I keep saying water, I mean liquid. Even though it's usually water. We can't always be certain of that. The mass of the liquid goes there. The specific capacity of the liquid is what we're looking for, the unknown. The change in temperature of the water is 13. The mass of the calorimeter by the specific capacity of copper, we were given that. The calorimeter is made of copper. By the change in temperature of the calorimeter there, remember this number and this number will always be the same. And I just do the maths and I work it out. I keep working it out and I get my specific capacity of the liquid is 2,110, just under 2,110 joules per kilogram per degree. Now, that isn't water. That is the specific capacity of oil. So it looks like that the liquid we used in this experiment was oil and not water. Again, if you, of course, put down in your formula water there, nobody would bat an eyelid. That's perfect, as long as you've got the formula correct. Now, where will we go next? Well, we're going to finish here with a question. It is from page 276, question 2 from your book. We just have a quick run through it. At this stage, you should run off, go back, learn what you need to learn from the video, and then go and actually do this question. Then come back to the video and see how you got it on. I will also probably post in Teams the answer and the little set of notes that I used to make this little video. So let's quickly run through the question and see where we're going with it. In an experiment to measure the specific heat capacity of a liquid, a quantity of the liquid was heated in a copper calorimeter by a heating coil. The following measurements were obtained. We've got the mass of the calorimeter plus liquid, so by subtraction we get the mass of the liquid. We've got the initial temperature of the calorimeter plus the liquid, the final temperature, so that we know the temperature of the liquid went up by 5 degrees Celsius and the temperature of the calorimeter also went up by 5 degrees Celsius. We're told the energy supplied, as measured by the Joule meter, was 700 joules. That is a capital J, believe it or not. So we're asked to do the following. We're asked to use these measurements to calculate a value for the specific heat capacity of the liquid, and that's the main part of the question. We're given the specific capacity of the copper being 390 joules per kilogram per degree. We're also asked to describe the apparatus that might have been used in the experiment. Describe in a Leaving Cert Honours paper is very much key for give a labelled diagram. So that would be the way to answer that, a labelled diagram of the apparatus we looked at the very top of this video. How might heat loss from the calorimeter be reduced in this experiment? Now, in a Leaving Cert paper, they'll always ask you give 2 ways or give 1 way or whatever. Here, it's left open, but I expect you to be able to write down at least 3 different ways that heat loss from the calorimeter can be reduced in this experiment. It's always a good plan, if you're asked for 2, by the way, to give 3. Don't give 4. Try to just give 1 extra than what you're asked. And a little question, explain why using a larger mass of the liquid while supplying the same amount of energy might have produced a less accurate result. I think we referred to something like that above, because a larger mass of the liquid clearly would result in a smaller rise in temperature of the liquid, and obviously percentage errors would increase there. So you run off, you do that question, then you come back to this video and we will see how you got on. Now, here are my workings out for this question. The first thing I did, of course, was I calculated in grams first the mass of the liquid used by subtraction, then I converted to kilograms, and then very easy subtraction, 18 minus 13, the rise in temperature of the liquid was 5 degrees and the rise in temperature of the calorimeter was 5 degrees. Armed with this information, then I put these values into the formula. So 700 was the energy supplied, mass of liquid, specific capacity of liquid is our unknown, we're looking for that, rise in temperature of liquid, mass calorimeter, specific capacity of calorimeter, and rise in temperature of calorimeter. I did the maths worked out, and I got an answer of 2,384.7 joules per kilogram per degree. That is, again, not water. That is, again, some sort of oil, because the specific capacity of water is around 4,200 joules per kilogram per degree, 4,180, whichever you want to call it yourself. Okay, hopefully you got that. For those of people that might find the maths challenging, I don't think you will, but if you did, remember, most of the marks will be obtained by students by getting to this line here, writing down the formula and putting things in correctly to it. Normally in an honours leaving cert paper, you're getting 2/3 of your marks by this stage here. The rest of the question was pretty straightforward. I've done the calculation again there for some reason. That's nice. And I actually haven't finished the rest of the question. I think that you should not find that too challenging. The rest of the question was here, draw a label diagram, give 3 precautions to reduce heat loss, and explain why a larger mass of liquid would cause a lower rising temperature of the liquid and more percentage errors. Okay. I didn't intend it to be this long, so I'll say goodbye, take care, and see you again some other time.